All right, if you're gearing up for a big competitive exam, you already know that general organic chemistry, or GOC, can feel like this huge, unbeatable mountain. But what if I told you that you could conquer it just by understanding a couple of core ideas? That's what we're doing today. We are going to break GOC down to the absolute essentials. Let's jump in.
You ever feel like you're just trying to memorize 1,000 different reactions and none of them seem connected? Yeah, you're not alone. So many students say GOC is one of the toughest parts of chemistry, and honestly, I get it.
But here's the secret. What if the entire, massive, complex world of organic reactions, all that pushing and pulling of atoms, is really just governed by one single fundamental concept?
And that concept, it's electron density. That's it. It's simply about where the electrons are and where they want to go. Think about it. An area that's packed with electrons, that has high electron density, is naturally going to be drawn to an area that's missing electrons. Once you start seeing chemistry through that lens, it all starts to click.
Okay, so how do we actually track where these electrons are going? Well, the first way is through something called the inductive effect. The best way to picture this is as a little game of tug-of-war happening right inside the single bonds, the sigma bonds, that make up the skeleton of a molecule. So let's talk about the rules of this game. First off, the inductive effect is permanent. It's always on. It works through those sturdy sigma bonds, and what it does is create these tiny little partial positive and negative charges. But, and this is super important, it's a short-range force. Its influence basically vanishes after about 3 carbon atoms.
Now this tug-of-war has two teams. On one side, you've got the -I effect groups. These are the electron hogs like nitro groups or halogens. They pull electron density toward themselves, which is fantastic for stabilizing any nearby negative charges. And on the other team, you've got the +I effect groups, like simple alkyl groups. These guys are generous electron donors. They push density away, which is perfect for stabilizing positive charges or cations.
Okay, so that's the theory. But let's be real. Knowing the theory is one thing. Applying it super fast when the clock is ticking in an exam, that's a whole different ballgame. And that's exactly why we have a simple framework, a kind of master key for solving these problems. Just remember these 3 letters, D, N, P. It's a simple little hierarchy. First, you always look at distance. The closer the group, the stronger its effect. End of story. If distance is a tie, then you look at the number of groups. More groups means a stronger total effect. And only if both distance and number are the same do you finally compare the inherent power of the groups themselves. All right, let's put DNP to the test right now with a classic exam question. We've got to rank these acids from most acidic to least acidic. Take a second. How would you tackle this? Okay, here's the key idea you have to know. Acidity is all about how easily a molecule can let go of a proton, which leaves behind a stable negative charge. Now, a +I group, which pushes electrons onto that negative charge, actually makes it less stable. And a less stable result means it's a weaker acid. So the bigger the alkyl group, the stronger its +I effect, and the weaker the acid becomes. And that's why this is the answer. Formic acid, option C, has no +I group at all, so it's the strongest acid. The propyl group in option B has the most powerful +I effect, which destabilizes that negative charge the most, making it the weakest acid by far. See how the order just follows that logic perfectly?
And guess what? This same logic applies everywhere. A positive carbocation, it loves getting electrons from donating +I groups. A negative carbanion, it gets stabilized by electron withdrawing -I groups. It's always about neutralizing that charge.
But the inductive effect isn't the whole story. Oh no, there's a much more powerful player on the field, the mesomeric effect. This one operates through the delocalized pi systems. You can just think of them as these electron highways made up of double and triple bonds. So let's put these two head to head. The inductive effect is this localized pull through single bonds. But the mesomeric effect, it's like a wave of electron density that flows through the entire pi system. That's why it doesn't care about distance and creates full actual charges. And here's the biggest takeaway. It is way stronger. And just like before, we've got 2 types. The +M effect is when a group with a lone pair of electrons, like an OH group, just donates some right into the system, flooding it with electron density and making it much more reactive. The -M effect is the opposite. A group with its own pi bond, like -NO2, yanks electron density out of the system, making it way less reactive. So when both of these effects are in the same molecule, who wins the fight?
This right here is the golden rule for your exams. The mesomeric effect almost always dominates the inductive effect. But there is one critical, super common exception you have to know: halogens. For halogens, their powerful electron-withdrawing inductive effect actually wins out over their weaker mesomeric effect. Burn that one into your brain.
Okay, let's bring it all home. Why does really, truly mastering just these two effects give you such a massive edge on your exam?
It's because of this number. Over 80%. Over 80% of the questions in general organic chemistry are directly testing how well you understand these electronic effects, how they control stability, acidity, basicity, everything.
You see, when you focus on the how and why of electron movement, you're not just memorizing a bunch of random facts. You're actually understanding the engine that drives all of organic chemistry. And that's the difference between just guessing and really knowing the answer. So, as you keep studying, I want you to try something. Look at every single reaction through this new lens. Ask yourself, can you spot the hidden tug of war? Can you see the electron highways? Because mastering this way of thinking is the real key to mastering GOC. Thanks for tuning in.